Today, I'm going to talk about experimental signatures of Hong's metal and the Hong's superconductor. I'll primarily focus on the iron-based superconductor, because there is a high TC there. Well, I'm Miao, by the way. I'm from Oak Ridge. So this project has been lasted for many years. We have a lot of collaborators working together on this project. From the theory side, we have collaborating with one of the best DMFT group, Gabby, Christian, Zhiping Ying. We also, work together with RPAS and STM group, Hong Ding from IOP, Peter Johnson from Brookhaven, Jiaxing Yin now is a postdoc at the Princeton with Hassan. We had some optical measurements together with Chris Holmes at the Brookhaven. And of course, we got a very good sample from Genda at the Brookhaven and the Changqing Jin from IOP. All right, so here's the outline of my talk. Since this is a superconductivity session, I think it's always good to start from a cuprate and try to build a connection from a cuprate to iron-based superconductors. The second part, I'm going to talk about evidence of Hong's metal, meaning I'm going to focus on the normal state of iron-based superconductor. I'm going to show experimental evidence of enhanced electronic interaction, orbital differentiation, coherent incoherent crossover. The last part is going to be the main part, of course, is going to be the superconducting phase, meaning how the Hong's metal really affect the superconductivity in iron-based superconductor in particular. Okay, so usually we want to start from the phase diagram, and we usually compare the phase diagram between cuprate and iron-based superconductors. If we start from the cuprate, the parent compound is widely believed as a multi-insulator or charge transfer insulator, depending on how you view the problem. If you dope your hole or electron, you actually end up a very complicated phase diagram. From the high energy scale to the low energy scale, you have pseudo gap, bad metal phase, strange metal phase. You have charge or spin stripe or density waves, and eventually you got high temperature superconductivity. And if you keep doping your system, and you end up in a Fermi liquid phase in the heavily overdoped side. So if we compare just the first look at the phase diagram for iron-based superconductor, you're probably gonna say, oh yeah, there's a lot of similarities. But if we look at it more carefully, then you see in the nominal parent compound, yes, you have antiferromagnetic order, but the antiferromagnetic phase is indeed a AFM semi-metal. So there's no insulating phase here. And if you start doping, you have very interesting phase, such as electronic pneumaticity. For some material, people can see strange metal phase, and eventually you got high temperature superconductivity. But the phase diagram definitely not as complicated as the cuprate. And if you keep doping, depends on which side you dope and depends on which material. For most of the time, you easily got Fermi liquid or superconductivity. For example, for the barium potassium system, you have a superconducting ground state all the way to fully potassium doped side. So there's no superconducting dome basically. So again, if we compare the phase diagram in the early days, people always say there's many similarity. So that's why we borrow a lot of concepts from the cuprate, but turns out there's more differences than similarities. The naive picture is, say, for cuprate, you start from 3D9, you have one electron, so you have very strong on-site intraorbital Coulomb interaction, which is basically the model physics. But for the iron-based superconductors, you start from 3D6. You have a multi-orbital, multi-band on the Fermi surface. So even just by naively guess, you wouldn't expect that's the model physics alone gonna explain everything. And if you're looking at the doped phase, so the cuprate, the ground state of the cuprate is highly intertwined, it's highly degenerate phase. So that's why it's so difficult to understand. But on the other hand, for the IMPES superconductor, it looks like a more metallic. The superconductivity always the ground state for most cases. So that's the differences basically motivate a lot of people, theorists, experimentalists, to propose different pictures. And among them, I think the topic that we're going to talk about, basically the Hund's metal or Hund's superconductivity, is one of the leading picture that's really explain experimental data very well. All right, so the Hund's metal physics can go back to, has a very, very long history. And you can go start from 1980s with George Sawatsky and Van Mario about atomic, atomic level. And you can also continue to, strongly correlated materials. So I put this reference from one of the organizer that's basically summarized the history in the paper. So you can always go there, find all the history, how the picture start evolve. But there are a few very interesting paper, I think very interesting to me at least. I think it deserves mention here. One is the Christian and Gabby's paper that made in 2008, where they basically study the Hund's effect in the ion-based superconductors. They find the so-called coherent and incoherent crossover, and they find the dominant role of Hund's coupling. The other work is from Philip Warner and Andrew Millis and their collaborators. Basically, they find what now called spin freezing regime, meaning the spin correlator does not go to zero if you go very long time. So that's basically, it's not for ion-based superconductor, but it's also very stimulating picture to see the new non-Fermi liquid phase. Another two, I think, very recent work, theoretical work. One is from DMFT plus an RGMET study. So what they are trying to understand the difference between Martinez and Hund's. I think it's a very, very good study in a sense. So it's basically from their study, they tell for the Martinez, you should have somehow significantly reduced density of state when you into the model physics, while for the Hund's metal physics, you still have a lot of density of state, meaning you never fully gap the density of state on the Fermi level. So this is stimulating in a sense. It can help us understand the battle metal phase and the coherent incoherent crossover. So experimentally, we always find the ion-based superconductor never really into the battle metal regime. It's always saturated at the Mott limit. So this is something that can explain the experimental data. The last one is more like pure mathematical analysis, CFD analysis of the model. So they can extract the exponent, how the local spin stability change with at the different energy scale. So that's basically clear the Hund's metal picture, which is if you imagine naively, you have orbital contour temperature and the spin contour temperature. These two temperatures somehow is different in Hund's metal phase. At high temperature, you first enter into the orbital contour temperature, but your spin still remain, spin freezing. So in that spatial regime, you have what people now call the Hund's metal physics. All right, having understood the basic development of a theoretical side, from the experimental side, we also keep understanding whether we can prove or disprove this Hund's metal physics is correct or not. Of course, we start from the normal state. And the first, I would say, quite interesting work from early days is by Luca Madesi and his collaborators, where he summarized some experimental data for 1-2 structure system. And you can clearly say, I don't know if you can see the icon or not, but you can clearly say the effective mass is basically increased from the electron doped side to the hole doped side. This is somewhat consistent with the Holmes picture because in the electron doped side, you are far away from the Holmes regime, while if you go to more hole doped side, you are closing to the Holmes regime. For us, we primarily focus on different family of ion-based superconductor, which is the lithium ion arsenic family, or people call 111 structure. So if you look at the left, it has natural cleaved surface. We choose this material for many reasons. One is because the natural cleaved surface is good for STM, for RPS. This material has very good resistivity. It has very small disorders. But more importantly, if you look at the phase diagram of this material, it does not have antiferromagnetic long-range order, but it still has decent high temperature superconductivity, and away from superconducting dome, you have a paramagnetic phase, which is ideal to study the intrinsic Holmes metal phase or Holmes superconducting phase. So that's primarily the reason that we study this 111 compound. So the first thing that we would like to study is the orbital differentiation, meaning the the dynamic response of electrons with different orbitals are different. So you see the typical RPS spectra, and we can identify the orbital characters by changing the incident photon polarization. And here the panel B is the Fermi surface. You see all three hole-like bands at the Brownian zone center and the two electron band at the Brownian zone corner. And you do see all the band has very strong polarization dependence. And based on that, we can extract all the orbital characters, which is summarized in panel C, where you see at the gamma point, the two, which we call alpha and alpha prime hole pocket, has primarily XZ and YZ orbital. The larger hole band, which has the larger dominant DXY orbital. On the electron side, you have the inner pocket primarily has DXY orbital character, while the outer side, which we call the delta band, has primarily DXZ and the DYZ orbital characters. Now, having established these orbital characters, then we can study the single particle response as a function of temperature. And you can see we choose two specific bands. One is the beta band, which has DXY orbital character, and the one, the delta band, which has primarily DXZ and DYZ orbital characters. So you do see as we increase temperature, the intensity of the band is keep decreasing, but more importantly, you see for the beta band at the 200 Kelvin, you almost cannot distinguish between the band structure and the background. On the other hand, for the delta band, although you see similar decrease of intensity, but you can still clearly distinguish the band structure from the background. So if we make a direct comparison, then here is the DMFT calculation. So you see the beta band as a delta band as a function for temperature. And you see for the beta band at a high temperature, you barely see the single particle spectral function. But for the delta band, you still see the intensity. So since this material is super clean, so that makes us to do a very reliable extraction of the spectral function. And you can clearly see in the panel A is the EDC's energy distribution curve. You see a very nice symmetric dispersion within a very narrow energy scale. You can extract the quasi-particle imaginary part, and you can extract the total spectral weight, meaning the integrated intensity. And in panel F, we summarize the extracted total spectral weight for the beta band in blue and the delta band in red. You see for the delta band, you does not really lose your spectral weight as you change your temperature. But in strong contrast, you see the beta band, which quickly lose their spectral weight almost 50% from 10 Kelvin to 250 Kelvin. So the solid line is the extracted number from DMFT calculation, which agrees very well with the experiment. So this data basically make us conclude that for the lithium iron arsenic, this particular compound, there's a very strong evidence that there's orbital differentiation. The second topic that we are trying to study is the coherent and incoherent crossover. That's, I just showed you in previous slides, where the resistivity start from a coherent or Fermi liquid-like to incoherent or saturation. Here I just show you 3 typical measurements. One is a potassium iron 2 arsenic 2, lithium iron arsenic, and the cobalt doped lithium iron arsenic. And you do see at a low temperature for iron potassium 2 arsenic 2, you have Fermi liquid at low temperature, but at the high temperature you start to saturate. So we can always define a artificial coherent and incoherent crossover, which is the peak position of the first derivative of resistivity right here. And you can track the coherent and incoherent crossover temperature change as a function of a fading number. Say here is 5.5 for iron potassium 2 arsenic 2, and 6.4 for cobalt doped lithium iron arsenic. And you see for endpoint 5.5, you have a much lower coherent incoherent crossover temperature, but for the electron doped side, it's go all the way up to above room temperature or close to room temperature, even though for this material you have a lot of disorders. And we measured a lot of material. We did the systematic doping dependence, and if you extract a number and plot a phase diagram like this, you see for doping at for more close to whole doping, you have a much lower coherent temperature, and if you go electron doping, your coherent temperature go up very quickly. So that's picture somewhat consistent with the early studies, basically show for a stronger homogeneous, you have a lower coherent incoherent crossover temperature, but for electron doped side, you have a higher coherent incoherent crossover temperature. All right, so I think all this data for this particular lithium iron arsenic put a strong evidence that for the normal state side, it does consistent with the Holmes metal phase. And then our question is how does Holmes metal affect superconductivity? So that's basically the motivation for our more recent study of superconducting phase. So again, I just want to talk in general about the pairing mechanism for the ion-based superconductors. We have been measured the superconducting gap systematically over several years, and for almost all ion-based superconductors. The one empirical result is that for all the superconducting gap, you can basically describe the gap function with a simple local form factors. The second evidence that we think it is strong pairing is we are able to measure a band, a superconducting band, a gap on a band that does not cross EF. As we're showing here, in the normal state, the band already below the Fermi energy, and you can still measure the superconducting gap and extract the gap size. So what we find is that even though the band does not cross EF, and in the weak coupling theory, you expect the gap goes to 0, but we still see a very strong pairing for those bands that does not cross EF. So all these results seems to indicate for ion-based superconductor, you do need a strong pairing mechanism. Then we noticed this very interesting paper by that time, which I think published in a similar time, where Jupin, Christian, and Gabby studied systematically the pairing mechanism in ion-based superconductors. Aside from the orbital antiphase pairing, there are 2 interesting information that we find very interesting. The one is they have a comment to say, because the off-diagonal part of the superconducting gap, they do expect the superconducting gap on band does not cross EF, which is identical to what we discovered experimentally. The second thing they comment is that the superconducting gap does follow a simple form factor, which is again consistent with our measurement. So based on this, I think it's good consistency between computation side and the experimental side, and to put a first evidence that the Hong's physics can affect the superconductivity in the ion-based superconductors. Then we keep digging in and study what else can we find. So an interesting observation is the scaling between the superconducting gap and the superconducting transition temperature. So similar map has been done by other people, but initially they were trying to put all the superconducting gap and try to scale with TC. I think it's, of course, does not work because ion-based superconductor is a multi-band, multi-gap system. You can never find a simple way to scale everything together, but the meaningful number, probably the largest superconducting gap for the system. So that's why we're trying to make the plot. And interestingly, you do find for all the bulk materials, the 2 delta max over kBTC does follow a simple scaling relation. There are exceptions, which is the monolayer iron selenium that is shown in here, the red line. For these materials, you can always argue the TC is not accurate, it's purely 2-dimensional, and there is evidence made by ZX Shen that there is a very strong electron-phonon coupling. So it's reasonable to expect for monolayer iron selenium, you have some deviation from other bulk materials. So then we posed a question to Gabby, how do we understand this universal scaling? And turns out there's a good idea that basically you can try to do the Elashberg equation, but instead of electron-phonon coupling, you put the spin fluctuation in there. This is the spin fluctuation correlator, but here you're gonna have an exponent gamma that depends on which system or what physics you want to work with. And you can plot the 2 delta max over kBTC as a function of gamma. And where is the Hong's metal physics could play a role. So which I want to, again, bring your attention about this DMFT plus NRG or CFT analysis, where for a large regime of energy scale, you have the omega 1.2 scaling. And now we are able to put the minus 1.2 into this equation, and you got it somewhere here. And this is basically corresponding to the Hong's metal point. And the 2 delta over kBTC is something about 7.5 or 7.6, which I consider is very nice agreement with the experimental data. So that basically tells us if you put the Hong's physics in your gap function, it does reproduce a lot of the experimental data. So the next step that we are doing is, as I just showed you, we basically, from experimental point of view, we justify the lithium or arsenic is a Hong's metal normal state, and we want to study whether the 2 delta over kBTC gonna still universal for these systematic studies. And here we can extract the superconducting gap from the RPAS for low dopings, and we can extract the superconducting gap also from the STM study, which has a better energy resolution and can go much lower temperature. Again, I just want to show how beautiful this material is. This is the STM real data. You see, for large region, you have no defect at all. And for the superconducting gap, it's homogeneous for a very large area. You do not need to worry about, statistically average your gap or find other way to extract your gap. The gap is there right away. So you can reliably get your superconducting gap, and you can reliably get your superconducting transition temperature. And here is what we extracted. For a very large doping and the TC from 0 all the way to 20 Kelvin, and the gap from 1.5 to 6 MeV, you have this beautiful scaling. again, that if you combine with your data at the normal state, that basically tells you the Holmes physics not only affect your normal state, but also play a role in the superconducting phase. And that's why we want to call it as Holmes superconductors. And I think I want to make a summary here. You might think I'm maybe too fast, but whatever. So we do find experimental evidence that's consistent with the Holmes metal. That meaning we do see an enhanced correlation, we do see orbital differentiation, and we do see clearly a doping-dependent coherent and incoherent crossover change. And in the superconducting phase, we find the experimental observations are very consistent with the physics that has Holmes physics in there. So I think I'll stop here, and thank you for your attention.
Okay, so now other questions, first from the audience here. Antoine has a question, so maybe you can. Oh, no, okay, so first André-Marie and then Antoine. What?
No, I mean, it's just that I don't understand what you mean by simply form factor.
Or the form of the gap as a function of K. Well, the question for you, Miao, is yep. What do you mean by simple form factor?
Oh, so it's basically the gap function delta K. So you can have cosine Kx, cosine Ky form factor. So that's what I mean form factor. You follow a simple next nearest pairing. If you expand, you have this cosine Kx, cosine Ky.
Okay, thanks. Now Antoine has a question. Antoine, he needs to unmute. Can you unmute
Can you hear me?
Yes, perfectly.
Yep. Okay, Miao, this was a fantastic talk. Thank you very much.
Thank you.
I wanted to ask a question about the very beginning when you show this very beautiful sharp quasi-particle peak.
Yes.
And I noticed that you actually can, exactly. So the upper left panel A, you seem yep. to be able to image that almost 10 millieV above Fermi level.
Yes.
Which is kind of wonderful. Is that just because the Fermi factor does not suppress the signal yet there, or what trick do you use?
Oh, it just simply divide by Fermi Dirac function. If you look carefully for 20 Kelvin data, we only above few MeV.
Yes.
But if you go higher and higher, then we can image higher and higher.
You can do that because it's for KT indeed. Okay.
Yes. Yes.
Okay. Other questions? If not, let's thank the speaker again.
Thank you.